Good evening. This evening I'm going to talk about one of the most powerful tools in medicine in this series on public health, and that is on vaccines. Millions of people are alive today because of vaccination. Some would have died in childhood without it. For many others, their parents, their grandparents, or other forebears would have died or been permanently disabled if they'd not had vaccination. And some of the examples of these, and we'll go through several of these, include tetanus, smallpox, diphtheria, measles, many causes of meningitis, and polio. For many people in wealthier countries, we often do not realize quite how much we owe to vaccination, although that would have been known really quite recently in the immediate past. And what we have here is a picture of people queuing for smallpox vaccination in the 1960s in Cardiff. All around the world, though, vaccination is saving lives in extraordinarily large numbers, and this talk is really about how that came to be. In addition to dealing with childhood diseases, which will be the first half of this talk, vaccines are also very important for our ability to deal with many epidemics and many adult diseases. So recent epidemics where vaccines have been important are COVID-19, which we're living through at the moment, and I'll talk a bit about that in the second half of this talk. Influenza pandemics, which I won't be covering, but vaccines are a major part of our armamentarium against that, and Ebola, where we now have highly effective vaccines that can be used when there are outbreaks. They're also able to combat many of the diseases of adulthood, including important infections, some of which are life-threatening, like pneumococcal disease, which causes pneumonia in older people, and some of them which are extraordinarily unpleasant in some cases, such as shingles. And increasingly, we're recognizing vaccination as one route to tackle some of the important cancers, of which the two most important at the moment are cervical cancer in women and liver cancer. Now, vaccination is actually, in many ways, a very natural process, because when you're celebrating vaccines, you're also celebrating the immense power of your immune system. Vaccines harness this power. Vaccines themselves do not kill viruses or bacteria or neutralize toxins. We do. So what a vaccine allows us to do is it allows our immune system to recognize that something is a major threat in advance of an infection, and it does this by mimicking an infection, and then much more safely allowing the immune system to respond to that so that when it first encounters the real thing, it can deal with it and jump on it and neutralize it or kill it extremely quickly. So it gives it advance warning that something dangerous might be coming. Now, I do not want to imply in this talk that vaccines are the answer to all infectious diseases. They're not. There are many infections where vaccines are not a central part of our response or any part of our response. Some examples of these are we have many major infections where we currently do not have a vaccine. And an important example of that is HIV disease, the cause of the last really major dangerous pandemic before COVID-19. For some, we have an okay vaccine, but we also have better countermeasures. Examples of these are cholera, where we've had for a long time vaccines, and typhoid, but we owe a lot more in terms of our control for cholera, for example, to good sewers and clean water rather than vaccination. On the right, I've illustrated this with the construction of the Great Sewers of London, which really were critical to defeating cholera. And then for some diseases, although we do have vaccines, the disease is not common enough to be worth vaccinating under normal circumstances. And some examples of that might be plague, where only a very limited number of people are likely to be exposed. It still exists as a disease. Or in the UK, in humans, rabies. We have good rabies vaccination, but there is not enough disease to justify this. But if you travel to a country where there's a lot of rabies, you should be offered a rabies vaccination. So sometimes we don't have a vaccine, and sometimes we don't need a vaccine because the threat is not great enough. But for many diseases, and many really appalling diseases, we do have vaccines, and we need to use them to reduce the threats. And when deciding whether to use a vaccine, we have to really consider three separate questions. The first is this disease a significant risk? If the disease is trivial, or if it is so uncommon you're almost never going to come into contact with it, it's probably not worth having a vaccine even if one is available. The second question is, how effective is the vaccine? And if you don't have a highly effective vaccine or a fairly effective vaccine, then it's really not worth vaccinating in many cases. So you need to have highly effective vaccines for significant diseases, and they have to be effective for long enough for the protection to be worth having. Some bits of immunity don't last very long. Some vaccines, a single vaccination lasts for a lifetime. So it is a very variable situation, but you need to have an effective vaccine, obviously, to be worth continuing. The third question is, what are the side effects? Most vaccines are actually extraordinarily safe. But if there are vaccines that have got significant side effects, that's got to be justified by the amount of benefit that people are going to get from them. So if you consider, for example, polio, this child is in an iron lung from polio, it was possible to accept a very small but real risk from the vaccination in the early phases, the early stages of the vaccination, less safe vaccines, because this was a very common, extraordinarily dangerous disease. So you need to be realistic about the side effects, and they've got to be small enough that it's still worth doing, because you then need to do a benefit to risk decision. There's got to be a significant benefit from the vaccine, and you've got to be sure that the risk is smaller than that benefit for the average person who's getting it. This is true for all of medicine. This is true for if you're prescribing a drug, if you're undergoing a major operation. It's always about what is the benefit compared to what is the risk. But the great majority of the vaccines that I'm going to be talking about today are extraordinarily effective against really unpleasant or very dangerous diseases, and they are very safe. The spur to vaccination was smallpox. Smallpox is an ancient disease, goes back a very long way, with major epidemics in Europe and elsewhere. And the more common form, variola major, had a mortality of over 30%, and in infants, over 80%. So this is a very dangerous and also very common, at that point, infection. Survivors were left badly scarred, and up to a third in some reports were left blind. So this is a very major disease. Now, it had been known since as early as 480 BC, so for a long time, that survivors were likely to be immune. It wouldn't have been called that at that stage, but there was a recognition if people had had the disease that they were at much lower risk of getting it again, and in some cases were asked to nurse the sick who had it. And this was a major cause of mortality around the world. Here in London, for example, in the 1750s, pre-vaccination, around 10% or more of deaths in London were due to smallpox. So this is a very major public health issue. The first steps towards vaccination were a process called variolation. Variolation was an early practice that was developed in Asia and Africa. And in this, pus from a pustule from someone who had smallpox was inoculated with a sharp instrument into someone who had not had the disease, into an area which was generally invisible under normal circumstances. And around 2% of the people who had this would contract smallpox and die, and in some of them, they would pass it on to other people, and it would cause an outbreak. But this was much better odds than natural infection, which had a higher chance of killing them and a higher chance of causing disfiguring, scarring, and therefore people were prepared to undergo this process. So here's an example of a very high-risk inoculation, not a vaccination, but a very high-risk process, but the risks of not having it were even greater. And this was introduced into Western Europe from Turkey by this remarkable woman, Lady Mary Wortley Montagu, also a writer and poet and adventurer. And she brought with her the embassy doctor who undertook a trial, a study, in prisoners in Newgate Prison, just up the road from where I'm speaking here, in 1721, that demonstrated it was possible to do this procedure, and then the prisoners survived, and when they were challenged with smallpox subsequently, they didn't get it. The prisoners were, at least under some circumstances, volunteers. But this, of course, was a very dangerous process. And the next step, and really the first and critical step towards proper vaccination, was undertaken a bit later by this remarkable man, Dr. Edward Jenner. It had long been known in folk wisdom that dairymaids and others exposed to an infection called cowpox from cattle did not get smallpox. And Dr. Jenner, who was a Gloucestershire country doctor, would now, I think, probably be called a GP, but also a scientific polymath. He was a remarkable man who became, for example, a Fellow of the Royal Society for his descriptions of cuckoos, looked at hedgehog hibernation, covered multiple areas of medicine, and also went ballooning. He was one of those people who did almost any scientific thing that came his way. But he was the first person systematically to study this. And in May 1796, he inoculated cowpox from a woman who had got it into an 8-year-old child, James Phipps, who otherwise would have had variolation. And James had very mild symptoms from which he then recovered. And when he subsequently had the variolation inoculation with smallpox, the smallpox did not take. He was protected. This is the first example of being able to use an extremely mild infection and use this to protect against a much more serious one. And Jenner continued to improve this technique, to promote it, to vaccinate the poor in his area. And vaccinate came from the word for cow, which is hence the name. And he also did observational studies, including a very important observation that people who'd had this inoculation with cowpox vaccination might get smallpox much later in life, so the immunity was waning to some degree, but if it occurred, it was much milder. And this observation by Jenner is important. And it's important, in fact, for thinking about some of the vaccines we're currently considering for COVID-19. Many vaccines are not all or none. That is to say, you may well have a situation where a vaccine prevents infection, you don't get any infection, or it may prevent significant disease, although you still get infected, or if you have significant disease, it may prevent you from dying, which you otherwise would have done without the vaccination. So vaccination is not an absolutely all or none effect. And this is illustrated by these two boys, both of whom caught smallpox at the same time from the same source. The boy on the right was vaccinated and has very, very minimal pustules. The boy on the left was not vaccinated, and you can see the result. So this is a situation where the vaccine significantly reduces the severity of the infection, even if it does not prevent it. And many vaccines reduce severity of disease, even if they don't stop infection. And the second thing from Jenner's observation is the effects of vaccines can wane over time. Vaccines for smallpox continue to work and continue to have a major impact on reducing smallpox, first in higher income countries and then around the world. And it got to the point where in 1959, the World Health Assembly, which is the formal body for the World Health Organization, agreed that we should, as a globe, try to eradicate smallpox. And at that point, roughly 2 million people a year were still dying of this disease. The vaccine used was very similar to the one used by Jenner. It was introduced by a very simple, what's called bifurcated needle, demonstrated here. and there was a global movement to vaccinate everybody. And over time, the map of places where there was smallpox shrank very considerably, and you can see the map 1967 on the left, all the way through to 10 years later. The last continuous case was in October 1977, and in fact the last lab case that was caught in a lab was here in the UK, in Birmingham in 1978. It is estimated that over 300 million people died of smallpox during the 20th century. After it was eradicated, no one has. And this major threat to humanity has completely gone. So this is the most extreme end of vaccination protecting against disease. None of us now need to be vaccinated against smallpox. The disease is gone. Several other vaccines were subsequently developed, and I'm just going to highlight two of them in the early years. The first of which is rabies. Rabies vaccine was produced by Louis Pasteur and Roux in 1885. This is an incredibly unpleasant disease with, for practical purposes, 100% mortality. And of all the infectious diseases I have seen, rabies is the one I would least like to die of. People die in terror, and it's a very unpleasant pleasant way to end your life. The initial vaccine that Pasteur produced was from an infected rabbit, and it was from the spinal cord, and he inactivated the virus by over a process of time. And then when a child was potentially infected, this was vaccinated into the child before they developed the rabies symptoms, and this was effective. But this was a relatively high-risk vaccine to use, so it was used in people who'd actually been exposed to a rabid dog, because almost all cases in humans arise from dog bites. The vaccine has now got steadily safer, so initially it was only broadly used in people who are incredibly high risk or had been bitten, but it's now safe enough to be able to use pre-infection, and if you travel to an area where there's a lot of rabies, you will be offered this vaccination against this very dangerous disease. A second use for the vaccine, however, was also to vaccinate dogs, and in areas where there was rabies in the wild animals, to put out bait with vaccines for example, foxes. And this has led to rabies, the map of rabies, gradually moving away and becoming smaller and smaller in area. So, for example, there's very little rabies now in Europe, none are here in the UK. So here's another terrible disease, massively reduced by this vaccine. There was a relatively old vaccine, but which has steadily become a lot safer. The initial vaccine was effective, but less safe. It has become steadily safer. And the third relatively older vaccine I'd like to highlight, largely because it's a centenary of it being used for the first time in humans, is BCG. BCG, so you have live virus, but a different species for cowpox to protect against smallpox. You have an inactivated, for practical purposes dead, virus for rabies. BCG is a live, related, but what's called attenuated, weakened mycobacteria. These are the kind of infection that causes tuberculosis, and it in fact came from bovine tuberculosis, again from cows. Still used today. It's fairly effective at protecting against tuberculosis in children, less so, for example, in adults, and it's not a perfect vaccine, but we haven't improved on it for TB at this stage. It is also highly effective against another terrible historical disease, leprosy. And it has led, it's been part of the reason why leprosy is a much less major disease around the world than it used to be. Now, a vaccine is really just a way of getting a lasting immune reaction safely. And before we come on to COVID vaccines, where things have moved on very rapidly in the last year, just consider some of the pre-COVID technologies that have been used, some of which, as you can see, were over a century old. Live-related viruses, like cowpox, a live attenuated but weak virus, or mycobacteria, like BCG, an inactivated virus, or dead bacteria, and the example there was rabies, a toxin, or come on to this, but an important example for that would be tetanus, where the disease is actually caused by the toxin that is in small amounts. But increasingly, we've moved to a situation where we don't have to use such large amounts of the infection. A bit of a protein from the coat of the virus or the bacteria, a complex sugar, what's called a polysaccharide, or a combination of the two, what's called a glycoprotein from the coat. And you don't therefore have to put in the full virus or the full bacteria. You put in this small part of it, and that's enough for the immune system to recognize it. And then when you get a proper infection, it will respond. And then with some of these, you have to also give something what's called an adjuvant, which helps stimulate the immune system so it recognizes that it actually needs to respond. And although people think of vaccination as always given by injection, and very many of them are, some of them are also given by mouth, and some of them can increasingly be given, for example, up the nose. So some children are vaccinated against flu by the nasal route, which is more acceptable, particularly for young children. So how do vaccines work? Well, the body is being assailed by bacteria and viruses, fungi and parasites the whole time. And it has multiple layers of defense, ranging from simple things like the fact your skin is very difficult to get through for infections, so a barrier, layers of mucus and things like that. It also has what's called the innate immune system. And this is when the immune system responds without having learnt about a particular infection. It just responds very, very actively against an infection, non-specifically and without memory. I'm not going to go into that in any detail at all because it's not relevant to vaccination, but is very important as to how you fight infections. But a third layer of defense is what's called the adaptive immune system. And this is much more specific to a single infection. And the adaptive system learns an infection, and then when it sees it again, when it again invades the body, it responds much more quickly and much more vigorously. The next time it is ready. It is this part of the immune system that vaccination uses. Those of you who've recently done biology will remember all of this in some detail, and I'm going to simplify an incredibly complicated and sophisticated system, which is the adaptive immune system. Broadly, what happens with a vaccination, as with an infection, is that particular cells, dendritic cells, present bits of the potential invader to other bits of the immune system. So they chop up bacteria and viruses, and they present them to antigen-recognizing T lymphocytes, which is the next stage of the immune system. And then two groups of cells, broadly, respond to that. T cells, including an important group called killer T cells, which will recognize this thing in the future and kill cells with it in, and antigen-producing B lymphocytes. And finally, they produce an important group called memory cells, and these survive for long periods, and then if they're re-exposed to the same thing, they respond again. And the T lymphocytes, the killer T lymphocytes, and the memory cells with the antibodies that they produce, that they lead to the production of later on, are the key things that allow a vaccine to prime the immune system, and then the next time it's exposed to a real infection, the immune system responds fast and in a very focused way. Now, often the immune system may need more than one go to get to the maximum amount of effect. And so many vaccines need a second or even a third dose to get the best protection and to maintain it over time. So the primary vaccination is like a first infection, and what you can see in this graph is you get an initial response, what's called IgM, that's not the bit that's really important on this, and then a rather larger response with antibodies with the IgG. But then if it's re-exposed, the second arrow on the right, then you've got a much larger response, much more quickly this time, on the second time round, and in a much more focused way. So the first dose is made much stronger and indeed more long-lasting by having the second dose. That's why it's very important that people who have a first dose of the vaccine, like the COVID vaccine, absolutely must get the second one as well if the vaccine they have is one that's designed for 2 doses, leading to a much more focused and stronger response. So that's the basics and the history of vaccination. And now I'm going to talk about some of the key vaccines in childhood. And I'm not going to go through all of them because there are too many for a single talk. But I do want to start off with a single vaccine, the 6-in-1 vaccine, as an example of one that's given here in the UK and in many other parts of the world. Here it's given at 6, 12, and 18 weeks old. And this covers 6 very major infections in an extraordinarily effective way. Tetanus, and it does this with a toxoid, so this is a toxin, an antitoxin response by the immune system. Diphtheria, also an antitoxin response. Pertussis, also known as whooping cough, which is an acellular type of vaccine. Polio, which is an inactivated virus. Hib, which is Haemophilus influenzae type B, which is a polysaccharide protein conjugate, so it's a bit of sugar and protein from the bacteria together in the vaccine, and hepatitis B, which is a bit of protein from the surface. And all of these are in this vaccine. And the result of this is they protect the child given it against 6 of the most dangerous diseases that they could be exposed to. Now, remember the 3 questions that I think were important to ask. Is the disease dangerous? Does the vaccine work? And is the vaccine safe? Now, all of these, the vaccines work highly effectively, and this is a very safe vaccine. But I just want to lay out why these are such important diseases to protect against. So in this 6-in-1, the first one is tetanus. Tetanus is the other appallingly unpleasant disease to watch someone with. It firstly is extremely dangerous in childhood. In rural communities without expert midwifery, infant mortality rates used to be incredibly high, up to 50%. I've illustrated this with St Kilda, where up to 50% mortality in infants was recorded within the not too distant past. And in some settings, tetanus can be the majority of these. If a child gets tetanus, then mortality will, under most circumstances, be almost 100%. And in adults, it's an incredibly unpleasant disease, which leads to very painful spasmings and often death, illustrated here by a famous painting by Sir Charles Bell of a soldier who had tetanus. The vaccine is a toxin which is inactivated. It's a toxoid, and that's because the thing which causes the disease is not the infection, but the toxin that the bacteria produces. And therefore, the vaccination is against the toxin. The vaccine's highly effective. It was introduced widely in the 1950s, developed a little bit earlier. Doesn't stop the infection. The infections still happen, but stops someone getting the disease. But because it's not stopping infection, it has no herd effect. So only people who are vaccinated are protected. People who are not vaccinated are not protected in any way. Very safe relative to risk of disease. Severe allergic reactions, which are treatable, are less than 1 in a million. And tetanus was very common in rural Europe and North America, and the rates came down very rapidly. So by 2019, only 4 cases, for example, in the UK. It used to be a very common disease. And there have been, thankfully, recent rapid drops in Africa and Asia. Maternal vaccination has almost eliminated neonatal tetanus. The second disease which this protects against is diphtheria. This used to be the 3rd leading cause of deaths in children in the UK in the 1930s. So there are people alive today who would have been children in this era. Case fatality rate up to 20%, and it's common. It's common throat bacteria where some strains produce a toxin. It has local effects on the throat, can lead to people finding it almost impossible to breathe, effects on the heart, leading to very dangerous heart rhythms, and effects on the nerves. So this is a very unpleasant infection caused with the damage caused by the toxin. And again, a toxoid in the vaccine, and that means the immune system recognizes the toxin and mops it up. First free vaccine in the UK, in England in 1940, and at that point there were around 2,500 deaths a year in children. You can see with that blue arrow when the diphtheria vaccine was introduced, the rapid reduction in cases, and by 1950, a decade later, only 49 deaths. And worldwide, there's been a massive reduction in deaths. Was over 1 million a year before the 1980s, has now very substantially decreased. The third vaccine within this 6-in-1 vaccine is polio. And two polio vaccines, an attenuated oral one, a live attenuated oral vaccine, and an inactivated injection vaccine, were both produced in the middle of the last century. And the reason this was important was polio was a common paralyzing disease. And the advantages of the oral version was it was easy to give, it was acceptable, you just put it on a sugar lump, or still do, produces good immunity, but can cause a bit of spread, but very rarely, about 3 per million doses, can actually cause polio-like paralysis. Much, much safer than actually catching the natural infection, but still a risk. The result of introducing these two vaccines is that polio, which was a rising problem in the US and a significant problem in Europe, disappeared incredibly fast, and that has actually gone away to a very large degree over the last bits of the last century. So by 2000, polio, which would have been a massive cause of paralysis and some substantial mortality, had gone down to incredibly low numbers. So if you look back to 1988, there were about 350,000 wild cases of polio. Last year, there were around 140, according to WHO figures. This disease is tantalizingly close to eradication, but not quite there. And that's been the situation for several years. Eradicating diseases is very difficult. And I gave a talk on that for those who are interested a couple of years ago at Gresham College. The other thing I wanted to show, though, with this map is the cases of wild polio are now restricted just to parts of Pakistan and Afghanistan. But there are still cases of paralysis caused by the oral vaccine, not the injectable one here used in children in the UK. Very small numbers of cases, but for this reason, the injectable form of the vaccine is also extremely important. The next thing in this extraordinary vaccine that children have is a vaccination against a bacterial infection, Haemophilus influenzae B, Hib. And this causes both meningitis and pneumonia. It was, until really quite recently, the commonest cause of meningitis in children under the age of 4. 1 in 20 died, so this is a dangerous disease, and 1 in 5 of those who survived were left with serious neurological disabilities. The vaccine was introduced in the UK in 1992, and it reduced the incidence extraordinarily fast by more than 90%. You can see with the arrow where the vaccine was introduced. And so if you compare the numbers, in 1991, 759 cases, by 2014, only 2 in this age group. And it also reduces carriage, which means people who actually carry it and can infect other people. So injecting someone else's children also protects my own family's children. And I'm glad to say, been a global program now since 2014 against this almost entirely preventable but potentially very serious disease in children. And the final one I wanted to talk about in the 6-in-1 vaccine was hepatitis B. This is a relatively rare disease in the UK, but a very common disease globally, and it can cause cirrhosis and it can cause liver cancer. It can be passed on 3 ways. Mother to child. If the mother's infected, she can infect her child. Then infected children can pass it between themselves by playing together, and then in adulthood, it can be passed on either sexually or by intravenous drug use, and occupationally for healthcare workers. It's a relatively rare cause of liver cancer and cirrhosis in the UK, but a major one in Asia and Africa with a very high mortality. The vaccine is 90 to 95% effective, and in Taiwan, for example, which had a lot of hepatitis B, the vaccination program for infants reduced cancer incidence by 80% and mortality from the cancer by over 90%. So it is an astonishing vaccine. So that's 5 of the 6 things in the 6-in-1 vaccine, and there are several other vaccines that children will get. Rotavirus, which is an oral vaccine against a significant diarrheal disease, which around the world kills many people, and you can see very clearly in which year this vaccine was introduced. Waves of rotavirus that occurred every year, predictably, largely disappeared when the thing was introduced. Meningococcus, which causes meningitis and septicemia, and pneumococcal disease. And then an important one, MMV, for measles, mumps, and rubella. I'd now like to move on to vaccines used in epidemics. And we have several different approaches to vaccines in epidemics. There are known vaccines against known infections. We get yellow fever epidemics from time to time. There was recently one, for example, in southern Africa, and we have a very good yellow fever vaccine which can be used. Known epidemic, known vaccine. Then there are epidemics we can get against a known infection that you need to adapt the vaccine, and an example of that is seasonal influenza and, from time to time, fortunately rarely, pandemic influenza. And there you have to adapt a known vaccine to a new variant of the disease. Then you can develop new vaccines against a newly emerging threat. So, for example, Ebola has been known for many years, but it wasn't until we had a massive outbreak in West Africa, which many people will remember, that we realized we needed to really push forward the development of vaccines, and Ebola vaccines have been taken forward and are highly effective. And then we need to be able to develop vaccines against new threats. And the most important of these now, by far, of course, is COVID-19. Finally, 2 additional ones. There are some epidemics where we might get a vaccine, Zika, for example, a recent major problem. And then there are some epidemics where we have struggled to get a vaccine, of which the most important is HIV. So we shouldn't assume that every time we have a major epidemic, we will always be able to get a vaccine. Sometimes that will not be possible. Now, if you have an epidemic, there are several different approaches you can take, but the thing you're likely to be faced with is that for at least some period of time, you're going to have a scarce amount of vaccine and a significant number of people potentially at risk. And there are broadly 3 strategies you can take. The first one is you can say, I've got a limited amount of vaccine, and I'm only going to give it to people who are at the highest risk because I don't have enough for everybody. And therefore, I'll try and find the people who are at the highest risk of dying, or the ones most likely to catch it, or the ones most likely to transmit it. So you identify high-risk people. The second approach you can use, and it was very effective with smallpox and was used also with Ebola, not relevant for COVID, is something called ring vaccination. And this works when you've got small numbers of cases which are easy to identify and a fast-acting vaccine. And you identify a case, and then you vaccinate everyone around them, the people they've come into contact with, and then you generally then vaccinate all their contacts as well. So you provide a ring of protection around the person who's infected. That's called ring vaccination, and that stops it spreading into the wider community. The third thing is once you've got enough people vaccinated, you may get population, what's sometimes known as herd immunity. This should only be considered as a policy goal in the context of vaccination, not in any other situation. And in that situation, because the great majority of the population have had a vaccine, if you've got a highly effective vaccine in the majority of the population, then when the infection wave starts, what you find is that because all the people around the person who might be infected are immune, the wave doesn't properly take off. So because everyone else is protected, I am protected, even if I have not been vaccinated or the vaccine has not properly worked. So these are the 3 ways in which you can use them: high-risk individuals, ring vaccination, and population vaccination. COVID-19 has seen the fastest development of vaccines ever. Old and relatively new technologies have been used, all of them aimed at trying to reduce COVID, and we've seen successes in multiple different classes. I'm going to talk about two of those because they're new, but I want to recognize that multiple different routes have all led to a successful vaccine. Relatively old-fashioned, highly effective things of using inactivated viruses. Protein-based viruses, again, a relatively well-established technique, and they're coming along, and there are now several in various phases of development. But two relatively new, and in one case very new, method in terms of actually using for this kind of situation, what's called virally vectored vaccines and nucleic acid vaccines. And I'll give examples of those two, because these are new technologies to be used in this kind of way. What all of them have in common, though, is these are simply a way of presenting to the immune system a protein or an other antigen of the COVID so that the immune system wakes up and the next time it actually encounters it, which might be with a wild infection, it will actually kill it or remove it from the system. Now, most of these vaccines for COVID-19 target the spike protein. So you all have seen photos or photomontages or models of the coronavirus with these spikes around the outside, and the very top of them, the very tip end of the spike, this is a kind of model of what that might look like in 3 dimensions. And the vaccines are against this spike, because these spikes are used by the virus to get into the cell. So they have to be on the virus, and they're a very good target for vaccination. And we've got some relatively conventional ones, whole inactivated viruses. For example, Valneva vaccine works this way. Protein and adjuvant one, example, the Novavax works that way. But the more recent ones, the viral vectored ones, Oxford, AstraZeneca, already being deployed here in the UK, and J&J Janssen, and RNA vaccines, of which the one being currently deployed in the UK is the Pfizer-BioNTech one. All of these are in the news, so I'm not going to spell out how they were produced. But I would like to just say something about the RNA vaccines and then the viral vectored ones. The RNA vaccine works on the idea of having the nucleic code for the spike protein, and in the case of the Pfizer-BioNTech vaccine, this is in a lipid, a fatty nanoparticle injected in, and that's incorporated into our own cells, which for a short time, because they then break this down very rapidly. This isn't incorporated into your own genetic code. This is a temporary thing. They produce the spike protein. And that's then expressed, and the body recognizes that this protein is a foreign protein, and then it mounts an immune response. And what you can see in this graph here, this is from a study published in the New England Journal, is in the dark blue lines are the people who are not vaccinated, and as you can see, numbers of cases steadily go up over time. And in the red line is the people who are vaccinated. In the small box, vaccinated once, up to their second vaccine in the bottom box over time. And what you can see is that after about 10 days, and initially they're the same lines, now after about 10 days, those vaccinated have almost no further infections. So the fact that they've had this protein expressed in the body has led to the immune response responding, and then when the wild infection arrives, the immune response just gets rid of the virus, and people don't get clinical disease. This is against clinical disease. And the RNA vaccines rather, have a huge advantage, which they can produce quickly. They can be reformulated very rapidly. So if we get a new version of this, we can quickly move on to that one. The other relatively new one, the other form that is being used here in the UK at the moment, are what is called virally vectored vaccines. And the concept of these is you have a relatively harmless or completely harmless virus, generally an adenovirus, which is a kind of cold virus. And the example we're using here in the UK The Oxford AstraZeneca one is an adenovirus called Chadox. It's a non-replicating, so it doesn't actually replicate inside you, just stays inert, chimp adenovirus, so it's not a human one. And it incorporates genes for the spike protein, rather like the RNA one. And then when it's taken up by cells in the body, they manufacture the spike protein. Again, this is seen by the immune system as foreign. Immune system responds, and then when the people are subsequently infected, the immune system recognizes very rapidly that they've seen this foreign invader before and gets rid of it. So this has only been used in a relatively small number of examples before. This is the first really widespread use of this technology. But both of these very rapid, highly effective vaccines. And you can see here, again, the blue lines are people who were in the control group, not vaccinated against COVID, and in the red, those who were. Now, when you start off vaccinating in an epidemic, vaccination initially mainly protects those who are vaccinated because you don't have any population protection. There's only a small number of people protected, because you've only got small amounts of vaccine. And therefore, it makes sense to vaccinate the people who are at the highest risk of coming to significant harm. And in the case of COVID-19, the very strongest predictor of this is age. And so the oldest people are by far the highest risk of dying, of going into hospital and having severe disease. And as you go down the age spectrum, the risk is much lower. So if you've got a limited amount of vaccine, you vaccinated the highest risk first, and the highest risk are the elderly. And if you think about this is a graph on the right that shows age bands of people, and in terms of who have gone into hospital, all of these people have gone into hospital, and then people who've died. Dark blue are people who've died, very lightest blue on the outside, people who've been discharged from hospital, and the group in between are people where we still don't know what the outcome is going to be. Most will be discharged, some sadly will die. And what you can see is the very oldest people have by far the largest number of people who die in the population. By the time you get down to the much younger ages, you actually have many few people dying, and if you get even younger, many fewer people going into hospital. So the biggest impact is by vaccinating the highest risk, who are the elderly. And if you think about UK data, over 80% of those who died were over 70 up to now. So therefore, vaccinating people over 70 is an absolute priority. But that doesn't mean that covers everyone who'd go into hospital. And around this constituted only just over half of those who went into hospital. So large numbers of younger people still have severe enough disease to have to go to hospital. So you start off with the oldest, and you go down the age bands. And you can think about it this way, which is, if you assume the vaccine was 100% effective, and no vaccine will be 100% effective, but if you assumed it was 100% effective, because such a high proportion of the very oldest people, particularly people in care homes, are at most risk if they catch this disease, you would only have to, if this vaccine were 100% effective, vaccinate 20 people in care homes to prevent a single death. If you took people over 80, you'd have to vaccinate 160 people to prevent a single death. If you chose people over 50, you'd have to vaccinate around 8,000 people to prevent a single death. And if you choose healthy people who have no other medical problems under 50, you'd have to vaccinate 47,000 people to prevent a single death. So what this shows is you get your biggest effect from vaccinating the oldest people. But what you hope is that as you move down the age bands, you soon get to a situation where, firstly, all the people who are most at risk of dying have been vaccinated, then all the people who are most at risk of being in hospital have been vaccinated. But the third thing you want is to reduce even the small risk of younger people having a very severe outcome, and sadly people have very severe outcomes and some people die even in the youngest age bands. But you also then start getting to a situation where enough of the population is protected that you actually have many fewer cases in the general population. The rates go right down, and that protects everyone. You get towards some form of population immunity. It may not be complete, but a long way towards that. So what do we know and what do we not know about COVID vaccines at this stage of time? So this talk is being given in February 2021. We know that natural immunity, and generally that's a good predictor of vaccine immunity, lasts at least 6 months. We know that there is much lower reinfection rates after a natural infection, but not none. So we do not expect that after vaccination there'll be no further cases. We think they'll be substantially reduced. We know that multiple vaccine types with the spike protein reduce infection. So it's not just one type of vaccine, lots of different types of vaccine all produce highly effective results. We know that this has got a good side effect profile, and data that has very recently come out in the UK, for example, implies that the rate of severe reactions is probably about 1 to 2 in 100,000, and these are ones which can be reversed. They're not necessarily in any sense long term, but 1 to 2 in 100,000, and for milder reactions, maybe 3 in 1,000. But these are things like feeling feverish, having pains, and so on. We are confident that immunity to severe disease is likely to be better than just to infection. So even if the vaccine doesn't protect you from getting infected at all, it is likely to lead to you having less severe disease. And we are confident that if we get mutations that get around the vaccine, we should be able to revise the vaccine relatively easily. What we don't know is how long the protection lasts, particularly in the elderly. We don't know how easily and rapidly COVID-19 escapes from the immune system, so evolves around it. We don't yet know what the impact of transmission is at an individual level, so you can't be sure if you're vaccinated that you cannot pass on the COVID to someone else. And we also don't know what the effect of large-scale vaccination is on transmission at a population level. So there are several things we do know with confidence, but there are also several things that we do not. But overall, what we're confident of is we have a highly effective and safe vaccine against a very major disease. And for this reason, this vaccine is being deployed in the UK and around the world. Finally, before I move on to the wider global issue, to recognize, and I'm not going to go through this in any detail, that vaccines can also protect not only against childhood diseases and epidemics, but prevent some important adult diseases. And the one I want to highlight is cervical cancer. Globally, around 500,000 women are affected by this cancer, around 3,000 cases a year in the UK. Often younger, this is a cancer which affects people in young adulthood, and is almost entirely preventable by a combination of vaccination and screening. A vaccine was introduced in 2008 against the two most common causes of the virus, HPV, human papillomavirus, which actually causes the cervical cancer, and that led to a substantial reduction in those viruses, but the other HPV viruses were unaffected, so demonstrating it has a very specific effect on this. And the vaccine effectiveness against these two most important ones was around 82%. And then subsequently, the vaccines have been produced which actually cover a wider range of the HPVs that can cause cancer. So they certainly work against the infection. Now, we know it's going to reduce the rate of cancer, and probably very substantially. How much it will reduce cancer will depend on how long the immunity lasts, and this is a relatively recent vaccine. We're confident it lasts many years, but does it last decades? What percentage of girls are vaccinated, because it's really essential they're vaccinated before they become sexually active, and what the effects are over time. And what you have here is some modelling studies that show that depending on how long the effect lasts, if it's a lifetime vaccine, then we will get an even bigger effect in reducing cancer than if it lasts for only a decade. But we are confident that this vaccine is going to substantially reduce this important cause of cancer in younger women. The number of deaths vaccines avert is remarkable, especially in lower and middle income countries. There was a recent study which came out this year which estimated the effects of vaccination against just 10 different diseases. This is not all the vaccines available. And their estimate was that between the years 2000 and 2019, so the last roughly 20 years, 37 million deaths were averted. And amongst children under 5 years, a 57% reduction in mortality, most importantly from measles. So vaccination has a massive impact globally. And we're increasingly moving to a world where the vaccines in childhood that I talked about earlier on in a UK context are available around the world, including in lower income countries, through a variety of mechanisms such as the Gavi system. There's been a delay between high-income countries getting the vaccines and low-income countries, and of course we should do everything we can to minimize that delay to as close to zero as possible. But there has been a very substantial increase in the amount of vaccination, very similar to the vaccines given here in the UK, in Africa, Asia, and Latin America. So if you look on the left, using diphtheria, pertussis, and tetanus-containing vaccines as a kind of marker, on the left you have 1981, and on the right, 2016. Red, less than 50% vaccinated. Blue, dark blue, more than 90% vaccinated. A transformed picture around the world, a really substantial improvement in vaccination rates. And the result of that is the number of child deaths caused by vaccine-preventable diseases has really rapidly decreased. And the improvement in child mortality is one of the great triumphs of public health over the last few decades. So if you compare 1990, almost 12 million children under 5 died. In 2017, that number was down below 6 million. And the coloured bars are ones which either are completely vaccine preventable or to a large degree vaccine preventable. And as you can see, those have come down very rapidly and will continue to come down because of the rollout of vaccines. So huge impact on child mortality around the world. So finally, Dr. Jenner's legacy. Dr. Jenner, by producing vaccination, a much safer way of preventing infections, led to many of the most feared diseases largely gone, where vaccines are available, substantial protection against multiple diseases of childhood, new and rapid approaches to responding to epidemics, as we're seeing now with COVID-19, major drops in adult disease continuing, including cancers, and vaccine science is advancing rapidly. I'm confident that vaccines will get more effective, safer, and increasingly may start to move into other diseases, such as cancers. A remarkable legacy. Thank you very much.